Okay, so this is part two of Joe Kelly 95-mile-an-hour curveball. The distance between the mound and the plate, generally speaking, is about 60 and a half, 60 foot, 60 and a half foot. So some of them are 60.6, some of them are 60.5 and a half, whatever. But we do want to know that how far or what path does the ball take? How far is that distance? I mean, we can't just say it's 60.5 because this thing is curving. And if it's curving, it should be a little bit longer than 60.5. So let's see how we can find this out. So if we use our S, if we use this as just being S in this direction, right? We know that ds dt is going to be equal to dx dt squared plus dy dt squared plus dz dt squared. And if we take the square root of that thing, then we can solve this thing. And basically what we're going to do is we're going to end up taking an integral. If we integrate ds, it's going to end up just being s, and that's what we're looking for. And if we integrate this horrible thing, dx dt squared plus dy dt squared plus dz dt squared, and if we take the square root of that thing and then we integrate this thing with respect to t, well, this would be our definition of what s would be. Well, most of the questions are, it's like, well, where are these things? What are these things? And how do we take the derivatives of these to get to these? Well, it basically comes from our r of t. So r of t is going to be equal to our velocity initial times the t, and this is going to be our I direction, which is our x direction, plus the 1/2 at squared, which is going to be our f divided by m, right, times t squared, and then plus our, 4 minus 1/2 gt squared. All right, this is our z, and this is going to be our j direction. So here we have our dx. So this is going to be dx. This will be our dy. We take the derivative of this thing, take the derivative of time derivative of this thing. And if we take the time derivative of this thing, we should be able to put our numbers in there. Hey, let's do that. So we know when we integrate ds, we're just going to get s, right? So this is going to be, s is going to be equal to the integral of the derivative of respect to time with vi is just going to be what? Vi, right? Easy, nice, easy integral. And then plus the integral of this thing, that the 2 is going to go away. And you're going to be what? Left with mf magnus divided by the mass times time. All right, so that would be that one. That would be this one. And then plus, well, the derivative of a whole number is 0. So this is actually going to end up being minus. Well, we'll just put it this way. Minus, plus, minus, well, the 2 is going to go away, gt. Right? And if we take the square root of that thing and then we integrate this with respect to t, and if we go between the time 0, which is basically time 0, and the amount of time it took the ball to go from here to here is what, 0.434 seconds. If you do that integral, I'm not going to do that integral here because I have too much respect for mathematicians. And if we do this integral, basically what we're going to get is s is going to be equal to about 60.6413 feet. So this does make sense. We know that this s is going to be slightly larger than this. Not much, but it's going to be slightly larger. So knowing that this s is slightly larger, that might change some things. I don't know. We'll see. But anyway, now we know that the actual path that it takes is actually 60.6413 feet. All right, so the next thing you want to know is, what is the curvature of this thing? I'll let you take a picture. The next thing we want to know is, what is the curvature? Well, the curvature of our particular S here is going to be it's a little complicated, but we can get through it. It's not a problem. We can do this. So let's think about this in terms of, if we look at this from the side, we're going to have our home plate's going to be over here, and our pitcher's mound is here, and the ball is going to be kind of going like this, and we know this is our Z, and we know this is our X, and we know in the Z direction is what, 1/2 GT squared. Actually, it's going to be negative, right? We know that path, and we know this is going to be velocity initial time. That's going to be our X direction. It's going to be 139.3 feet per second. So if we know this is our R of T in here, right? This is our R of T, and this R of T is moving with the ball, so the R of T is going to be changing. So it's going to start here, and it's going to change. So we know that if there's an angle in here, right, this is what we call this phi. This phi has to be changing. It's not going to remain the same. It's this point is moving, and the R is going to be down here, so then phi will be smaller. Well, if we look at this and use the good old Pythagoras theorem, right? If we look at the tangent of phi, so the tangent of phi is going to be what? Opposite over adjacent. So that would be negative 1/2 GT squared divided by the adjacent, which is velocity initial T. Okay, so we found the tangent. If we find the tangent and we know this is moving, we can take the time derivative of this thing. If we take the time derivative of this thing, it's really, really, really important not to just put down secant squared, because that is the derivative of tangent. But you got to realize that you're going to be using the chain rule here, because this thing is moving, it's changing, right? It's not static. If this thing is static and you take the derivative, okay, then it's going to be secant squared, yes. But this thing is moving. So when you take the time derivative of this thing, you're going to get a secant squared, that's right. You get a secant squared phi, but now you got to bring along d phi dt, right? And that's going to be equal to, well, the time derivative of this thing is going to be what? Negative gt. And then the time derivative of this thing is just going to be velocity initial. Hey, what did we find right here? Well, we found how much this thing is changing in time, right? We found this thing. This is what we were looking for. This tells us how much this thing is changing in time. All right, so let's solve it. Let's see what we can get. So d phi dt is going to be equal to our negative gt divided by velocity initial times 1 over secant squared phi. Well, that's nice, but what's it going to do for you? Well, let's look at secant squared of this thing. Just look at secant. Secant is what? Hypotenuse over adjacent. I'm pretty sure of that. Hypotenuse over adjacent. So my hypotenuse over adjacent. Now don't forget, this R of T, we're just looking in the Z and the X direction. We're not worried about Y. We're looking in the Z and the X direction. So that R of T is going to be what's happening in the Z and the X direction. So if we look at our secant, our hypotenuse is going to be this thing, and then our adjacent will be this. Well, okay, then all we got to do is take what the hypotenuse is, R of T squared, divided by VT squared. And that would be this thing, right? But if we have a 1 over it, we actually have 1 over secant squared phi, right? That's going to be adjacent over hypotenuse. So we can just kind of like get rid of this and put it adjacent over hypotenuse. Well, that would mean that adjacent is this thing over this thing. So this is the adjacent, this is the hypotenuse. All right, let's do that. So d phi dt is going to end up equaling negative gt divided by velocity initial, right? Well, let's look at the adjacent over hypotenuse. Well, the adjacent is this thing, which is what? 4 minus 1/2 gt squared, right? And that's going to be this thing. And then we're going to be dividing it by our what? Velocity initial t. Sounds about right, but we got to square this thing, and then we'll be dividing it by our velocity initial t. Oops, I did that wrong. This should be switched around. Durr. Love being physics. I love teaching physics because it teaches you so much. I switched that around. It's going to be velocity initial time divided by our velocity initial plus our 4 minus 1/2 gt squared. There we go. There we go. That makes sense. And then we're going to square this thing. And then we're going to square this thing because this is a square. All right. Okay, let's keep on going. We're almost home. Got that right. So now d phi dt. Well, we can start cleaning this up a little bit. I know this is a velocity squared, so this velocity stays, this velocity goes. This is a t squared, so this is going to end up being a t3, so this thing basically goes away. So we have a velocity initial up here. And let's go for that. So we have an initial, we have negative g t cubed, velocity initial, divided by all this crap, velocity initial t plus 4 minus 1/2 g t squared. And don't forget, we got to square this thing. I think you want this the other way around. We got to square this thing. That's our d phi. That's going to be the change. This equation is basically going to be the change in this angle. This is going to tell us how much of a change there is in this angle. Let's clean it up a little bit so that we have this equal to d phi dt. So if we know velocity initial, if we know some time, and that's all we need to know, we can figure out what d phi dt is. Now, since we know that, I'll let you take a picture, or you can take a picture if you like. Since we know that, now we can find the curvature, because the curvature is going to be d phi dt divided by ds dt. Well, we already figured out ds dt, so we can just kind of like plop that all together. So let's do that. Let's put that all in one big baby. All right, so my curvature of this particular pathway, usually make it a little k, is going to what, be d phi ds, which is going to be what, d phi dt divided by ds dt. All right, that's going to be my curvature. All right, let's look at that. So curvature, I know my d phi dt, and that's going to be that horrible looking thing. It was minus g t cubed velocity initial divided by velocity initial time plus 4 minus 1/2 gt squared. And you got to square all this thing here. And now we got to find ds dt. We already know that. So that's going to be what? Dx dt squared plus dy dt squared plus dz dt squared. I always run out of room. Let's try it again. So this is going to be times dx dt squared plus dy dt squared plus dz dt squared. And then we want to take the square root of that thing. Well, no, nope. We don't want to take the square root of that thing. We want to multiply this thing because this thing is on the bottom, and we know it's a square root, so this would just be negative 1/2. There you go. That's it. That's your baby. That's the curvature. That's going to be the curvature of a curveball. Whoop. That should be a curvature of a curveball. Keep this squared over here, and this is going to be multiplied. So this will be like this. This will be over here. This is squared, and this is times this thing. Okay, great. So now we know the distance, we know the actual path, and then we know the curvature. And again, we know these things. We know our dx dt's, we know our dy dt's, and all that good stuff. All right. I hope that helps. Gotta love physics. And please subscribe.